Chemistry. So let's start with the basics, and the most basic you could possibly get in chemistry is a single atom. A single atom which we can divide into two different parts, something which I like to call the massive part and the reactive part. The massive part is the nucleus right in the center, and the reactive part is the electron cloud around the nuclei. So let's start simple with the nucleus. In the nucleus of the atom we have protons and neutrons. So first things first, protons. The number of protons dictates the atomic number. So the number of protons, that's what the atomic number represents. This atomic number tells us which atom we're talking about. So 1 proton is hydrogen, 2 protons it's helium, 8 protons it's oxygen. One small issue, however, because you see, in reality, if you actually tried combining 8 protons together, then you wouldn't really end up with oxygen. Only you'd end up with an explosion. That's because protons have positive charge, which means that they repel each other. So we basically need something to bind them together, and that something is called neutrons. That's why neutrons are needed inside of the atom, but still there is a bit more depth to it, because the mass of a proton is equal to this, or 1.007 atomic mass units, or just around 1 atomic mass unit. For neutron, it's equal to 1.008 atomic mass units, or just once again around 1. My point being that they are both really similar in mass, so another value I'm going to throw at you is the mass number, which is just equal to the number of protons plus the number of neutrons. So let's revise. We have the atomic number, which is just equal to number of protons, and then we have the mass number, which is equal to number of protons plus the number of neutrons. If you change the atomic number, you change the atom, and if you change the mass number, so the different number of neutrons, you change the isotope of an atom. That's what isotopes are, just different amounts of neutrons. But here's the million-dollar question, however. Why does the number of protons define the atom, not number of neutrons? When you change neutrons, it's the same atom, different isotope. Why is the atomic number equal to protons? Well, it's because neutrons have neutral charge and protons have positive charge, and since opposite charges attract, protons are magnets for the negatively charged electrons. Now, I like to call the electron cloud, so the place where the electrons are, the most reactive part, and there are a couple reasons for that. Mainly the fact that electrons are charged and far away from the nucleus, which means that it's mostly them which are responsible for all the reactions. And why different types of atoms like hydrogen or oxygen or lithium are so important. Because the name of an atom tells us the atomic number, which in turn tells us how many protons an atom has, which in turn tells us the charge of the nucleus, which in turn tells us how many electrons an atom has, which in turn tells us how the atom will interact with other atoms. But how should these atoms interact actually? That's a good question. In order to answer that, we'll first have to talk about the electron junk. All of the electron junk, because the electron cloud can be divided. You can divide the electron cloud into different shells, which can be further subdivided into subshells, and further divided into orbitals. Orbitals, let's leave them behind for now. Alright, first we should start with shells. So, what are shells? We can think of shells as different orbits that the electrons are taking. So just like moons orbiting a planet will have different distances, the electrons orbiting an atom have different shells. Except electrons don't really orbit, they just kind of cloud around the atom. So what are the shells representing? Okay, take a look at this chair. If we take a ball and chuck it, it's going to stay mid-air. Obviously. Right? Well, actually no, we all know that the ball will fall at some point, and that's precisely what's happening to our electrons. Just like this ball is attracted down due to Earth's gravity, the electrons are attracted to the nucleus. The ball wants to get rid of as much potential energy as it can, just like our electrons. For the ball, this means falling down. For the electrons, it means falling into these different shells. But there is something different about our example, because you see, unlike our ball, electrons cannot have any amount of energy, only they can have certain discrete values. So if we were to adjust it into our example, you can imagine the ball falling because there is no other balls below it, so it's not occupied. But if it were occupied, it could only have this discrete energy level, so it's either the ground or the chair, nothing in between. So that's how we can think of shells, as the places where electrons reside, the final destination where they fall, where they want to be on the shell with the lowest energy state. Now what about filling these shells? How does that work? Well, just like filling a box with balls will mean first the lower layers and then moving on to the higher ones, filling shells means starting with the lowest numbered shells and going up. So increasing the atomic number, we have first electron on the first shell, second on the first shell, on the second shell, third, fourth, fifth, sixth, seventh, eighth, ninth, 10th, then third shell, 11, 12, 13, 14, 15, 16, 17, 18, moving on to the fourth shell, 19, 20, and then back to the third shell. That seems rather weird. That seems rather weird and bizarre, doesn't it? I mean, why are we going up a shell and then back? Well, that's because electrons on a single shell do not have the same energy level, and that's why we need to divide it further into subshells. That's why we need subshells, because in subshells all electrons have the exact same energy level, and so the true filling order would be relative to subshells, but the way we fill those is still a bit annoying to visualize, so let's switch to a different method. Right here you can see all of these different shells and their appropriate number. Really often chemists will use letters to represent these numbers, but that's only because chemists hate math, and so their burning hatred is expressed by removing as much of it as possible. Now, how many electrons can we fit onto each shell? That's simple. The answer is 2n squared, where n is our principal quantum number, or just number of the subshell, whatever you think sounds cooler. So for the first shell, it would be 2 times 1 squared, so 2. Second shell, 2 times 2 squared, so 8. Third shell, 2 times 3 squared, so 18, and so on. This should all seem simple enough so far, but what about these subshells? I mean, I just mentioned that the filling order is dependent on them, not the shells. In order to understand subshells, we'll need to divide all of them into subshells. How many subshells can we fit into each shell? That's a good question, and the answer is the number of the shell. So 1 subshell in the first shell, 2 in the second one, 3 in the third, 4 in the fourth, and so on. Now, how many electrons can we fit onto each subshell? Well, for that we'll have to index the subshells. We index them starting with a 0 this time. Once again, chemists really often like to replace these numbers with letters, but this time they replace them with letters even more often than last time, so I'll put them on the side like that, because that's kind of important. Just like with shells, we also have an equation for filling subshells. It's 2 times 2L plus 1 in brackets, where L is the azimuthal quantum number, or just the subshell number, once again, whichever you think sounds cooler. So once again, we can fill all of these subshells in the same way, and there we go, that's the maximum number per subshell. Okay, now we've got all this out of the way, it's time to finally answer the question of what is the filling order. And so I can describe the filling orders of subshells to you in two ways. First of all, with an equation, so if you have an atom with a certain amount of electrons and you want to add one more electron, then you just look for the subshell with the lowest, n plus L, prioritizing the n. And whilst it is a solid way to describe it, almost everyone prefers the graphical explanation, which is this. That's the filling order for electrons. So going back to our original example, you can see that after filling the third shell's first and second subshell, we move on to the fourth shell before filling it some more. So we go to the fourth and then back. And now there are two more things left to mention about the electron configuration, which is first of all how we note it down. And we note it down with subshells. So with magnesium, for example, we start with the first shell, first subshell, then second shell, first subshell, second shell, second subshell, third shell, first subshell. For each of these, we note down the shell number, subshell letter, and the amount of electrons on it. But this sort of notation gets really large for the larger atoms, so for magnesium we could also note down like this. So the electron configuration of neon plus 2 electrons on the third shell, first subshell. Another thing I'd like to mention is the valence shell, or just the outermost shell for the third time, whichever one you think sounds cool. Valence shell will be important later on, but what I'd like to focus on right now is that because of the way electrons fill into shells, you can never have more than 8 valence electrons. That's because if you ever have 8 valence electrons on the valence shell, then instead of filling the third subshell, you move on to the next shell. and the next shell becomes the new valence shell. And I know it's a lot of words, and calling these two shells and subshells isn't making it any clearer, and if not for Manim in this video, it would be a lost cause. But if you understand this, then you understand everything you'd need about electrons and electron configuration. Omitting orbitals, that's a topic for another video. So let's go over a couple of examples, starting with lithium. The atomic number of lithium is equal to 3. And since we're not talking about any isotopes, its mass number is equal to 6. So based on that, we can tell that it has 3 protons, 6 minus 3 neutrons, and 3 electrons. Where will those electrons go? Well, starting with the first shell, first subshell, we put 2 of them there. And then second shell, first subshell, the remaining electron. That's lithium electron configuration. Now let's tackle something larger, like potassium. Potassium has atomic number equal to 19, so 19 protons. Once again, non-isotope, so the same number of neutrons, or just double mass. Except the more massive the atom gets, the higher the ratio, which means that in order to get a stable atom, we actually need 20. Since 19 protons, also 19 electrons. Now, where will those electrons go? Well, you already know this. 2 to the first shell, first subshell, 2 to the second shell, first subshell, 6 to the second, 2 to the third, first, 6 to the third, second, and the 1 electron onto the fourth shell, first subshell. But before we go on, here's the thing. This whole electron configuration is a serious mess. But if you recall earlier on in the video, you realize that we can simplify this a bit by, instead of going subshell by subshell, saying that this electron configuration is equal to the electron configuration of previous noble gas plus 1 electron on the fourth shell. There, isn't this much simpler? Now using this method, we can go for the really big guys, like palladium. Because palladium is really large, atomic number of a whopping 46, and you know the deal by now. 46 protons, 36 neutrons, since we hate isotopes, once again we need the additional 10 because it's so massive, 46 electrons, because the same number as protons, and we could go subshell by subshell route, but with this many electrons it would take ages. So what we can do instead is we can check what's the last noble gas electron configuration like, and paste it in. Now we're left with 10 electrons, so we just continue the pattern. 2 electrons onto the 5th shell, first subshell. 8 onto the 4th shell, third subshell. Wasn't that a much easier method? And actually, when it comes to electrons and atoms and all other things like these, that's pretty much it. There isn't really much more to add, so now we can move on to... What? No, that doesn't make any sense. It can't be 10. It cannot be 10. Yes, palladium has 10 electrons on its valence shell. And if you pay close attention and you've actually walked through the rules, then you might realize that it doesn't make sense. It goes against them. From what I laid out, it really seems like 8 valence electrons is the limit. But palladium has 10. Why is that? And so here we come to the problem of quantum mechanics versus chemistry. Because you see, chemistry is not the most basic kind of science. If you want to go more in depth, you'll reach quantum mechanics, which describes the behavior of atoms even better. And yeah, if you don't like exceptions, because there are plenty of exceptions in chemistry, if you don't like exceptions, if you don't like these general rules, if you want to be specific, exactly, and get the perfect answer, quantum mechanics is for you. But there is a downside. You see, if you want, for example, a perfect answer of how 2 oxygen atoms would behave when they are bonded together, yes, you can get that with quantum mechanics. You just have to wait like a couple of decades to get that answer, and that's why chemistry exists. It's because quantum mechanics is just straight up too complex to apply to reactions that are this massive. And yes, even just between 2 atoms, that's already massive in comparison to quantum mechanics. And that's why we have chemistry, and that's why we have all these rules, all these exceptions, all these general ideas. But I don't want you to get the wrong idea, okay? All of these rules are based on quantum mechanical theory, alright? All of them. And it takes a lot of work to actually create such a rule. So the fact that they seem so simple, the fact that they are so simple, just shows their genius, describing all of these psi functions, differential equations, integrals, probability and other junk with just multiplication and addition is impressive. But it will always lead to some problems. These problems being exceptions and rules breaking. But that's the reason why people are always upset with chemistry. And it's not really chemistry's fault. We just haven't done enough scientific research to get there. We don't have a standard unified theory of atoms in which we can just plug in the electrons and plug in protons, neutrons and get the position of everything. No, that's why those are your two options. It is so large and massive that would take us a century at least to get the point of reactions or exceptions. Those are the only two options. And so that's why we have models in chemistry. Models. Oh boy, wouldn't that be just a perfect segue to bonds. But first out of the way, a quick word about orbitals. The way they interact and their specific behavior is a bit difficult to explain, but all you need to know is that subshells have different shapes, and those shapes are kind of called orbitals. You can think of them as a shape of probability of charge distribution. That should clear it all up. Anyhow, I just want to mention orbitals briefly because here's the basic idea. Electrons are negative, protons are positive, both of them attract. So if we have two hydrogens, for example, both of them have a proton and an electron, all of these protons repel each other, just like electrons do. But each electron attracts a proton. Now, even with the smallest possible atoms, this is still an extremely difficult problem, especially when you consider that this is still a simplified version of how it actually works. So we need to simplify everything as far as possible. Here's what we're going to do. First of all, we can disregard all electrons and just leave the ones on the valence shell. Now, remember the thing I said about the valence shell and how due to the filling order they normally never have more than 8 electrons on them? Well, that makes atoms really like number 8, which is called the octet rule. I'll make a whole video about bonding soon, about this whole Lewis fella and how orbitals actually interact, but for now let's leave it there. For example, carbon dioxide. With 2 oxygens and a single carbon, oxygen having 6 valence electrons and carbon having 4 valence electrons. This means that oxygen is missing 2 to its 8 and carbon is missing 4 to its 8, which means that we can just move them together and there. Now carbon and oxygen can pretend to have an electron configuration of neon. And since noble gases are really stable, they can basically pretend to be stable. Oxygen has 8 valence electrons, carbon has 8 and oxygen has 8, and these bind them together covalently. Covalent bonding is based on 2 concepts, valency and co. Valence is a bit of a vague term again, but it basically refers to how atoms bond using valence electrons. Co in this case refers to 2, so basically how 2 atoms bond together using pairs of electrons. Seems simple enough, and that's because it is. It really is simple. But as I mentioned multiple times, we're dealing with models, so we need to be more specific. That's why we have further subdivisions into sigma covalent bonds. Sigma covalent bond is formed when atomic orbitals overlap head-on. Remember orbitals? Those are the shapes of subshells. Now this would be different from something like a pi bond. Pi bond which would look like this and is formed when 2 lobes of an orbital on one atom overlap with 2 lobes of an orbital on another atom, in which the overlap occurs laterally. So like this. Like this animation should make it clearer. But what if you don't want to join 2 atoms, only 3? Well then, the 3-center 2-electron bond is for you. Or maybe 4-center 4-electron bond. Or maybe bent bond, the banana bond, or agoistic interaction. There is a lot, and the thing is, most of them are niche. And I could go in detail, but there is no particular point. Covalent just means share electrons in pairs. And that's all you need to know about this one. Next we have metallic bond, which is a bit more exciting because here's what happens with metallic bonding. With metallic bonds, you have metallic ions, which are basically imbalanced electrons, some atoms that do not have their charge balanced between protons and neutrons. In this case, they are cations, so positively charged ions, which basically means atoms missing electrons. Now, since they are charged, it means that they actually actively repel each other and will attract electrons. The cool bit being, of course, that if you pour a bunch of these ions together with a bunch of free electrons, each of them will want to be as far away from themselves and as close to the opposites as possible, leading to this. So whilst covalent bonding, atoms bond together to achieve stability on their valence shell, with metallic bonding it's created due to attraction between ions and electrons. This leads to the bond being extremely strong, which in turn leads to certain properties of metals, like for example high boiling points. Also, the general loose structure of metallic bond, so the electrons being free, leads to some other properties like their malleability and I'm certain this won't come up later, conductivity. Now, the last kind of bond we'll cover today will be the ionic kind, and here's how it works. We have a sodium atom and a chlorine atom, and they are in an interesting spot. Both of them want to have the electron configuration of a noble gas, but sodium has one too many electrons, and chlorine is missing one. So what basically happens is sodium pretends that its electron actually belongs to chlorine, and this way sodium pretends to have an electron configuration of neon, and chlorine pretends to have the electron configuration of argon, but this electron still very much belongs to sodium, and that's how they bond. Kind of. This obviously is an oversimplification, just like the rest of this chapter, because bonds are really complex, but that's the basic gist of it. Except there are two more things I'd like to mention. First of all, this is the absolutely worst bit of chemistry. Not because it's difficult, or because it's complex, or because there are exceptions. No, this is the absolutely worst bit of chemistry because the naming convention is absolutely bloody awful. Okay, yeah, this is my opinion. I suppose I should make that clear, but still. You have the positively charged cation and negatively charged anion, but because the number of protons determines the atom is the number of electrons, which actually changes for ions, which is negatively charged, which means that the positively charged cations have less electrons and negatively charged have more, which means that if you see a plus, it means less. If you see a minus, it means more electrons. But that's just my opinion, that's just my bit. I have plenty of things to be upset about in chemistry, so I should clarify this is just opinion time. But the second thing, which is the vague significance surrounding ions. Due to how often they are used in movies and games, the word ion carries a lot of weight with it, even though they aren't really all that mysterious and hyper-scientific. I mean, don't get me wrong, they are cool and by design have an imbalance within them, and since we live in a universe where useful energy is directly linked to the imbalance between values, this leads to a lot of fun uses for them, but they aren't really that much different from ordinary atoms. They are ordinary atoms, just with a different number of electrons. So that's what you should remember about ions, alright? That's all they are. And that's cool and all, except it's all theory, and whilst knowledge about atoms and bonds is certainly useful, it would be a bit weird if some random guy on the internet who just overuses Blender tried to tell you anything about practical chemistry, and actually using chemistry. So I'd like to introduce someone who isn't just a random nobody, only an expert when it comes to electrochemistry. From the YouTube channel Scrap Science, it's Scrap Science!
Hello, it's Harry from the channel Scrap Science. You've probably never heard of my channel, but I do chemistry videos and various related things. I'm a fan of MAKiTs videos, and so here I am ready to talk about the next level of complexity for this chemistry-oriented video. Let's get right into it. So, the first question you might ask now that you've got all this expert knowledge of chemical bonds is, how does this bonding stuff apply to chemicals in the real world? And that's a very difficult question to answer in a simplified manner, because almost all matter, but not quite everything, is basically built and put together with chemical bonds. A more appropriate question might be, where doesn't this bonding stuff apply to chemicals in the real world? Now that's a question we can actually answer quite easily. The only things we commonly interact with that don't give us chemical bonds in some description are the noble gases, as mentioned before. These elements already have a particularly favourable electron configuration, so none of them feel the need to form bonds to make themselves more stable. If you think of the gas inside a helium balloon or in a neon sign, the atoms in there are all just hanging about by themselves, never forming any kind of chemical bond with anything else. But this is boring. We didn't come here to talk about the things that don't form chemical bonds, we came to talk about the things that do. And seeing as that's the vast majority of all of the matter we interact with on a daily basis, we've got a lot to get through. Let's do this in the same order as the bonds mentioned before. So covalent bonds come first. Covalent bonds are everywhere. When atoms are bonded together by covalent bonds, we have what's called a molecule. Starting simple, water, you've probably heard of it, is a molecule consisting of an oxygen atom bonded to hydrogen atoms through sigma covalent bonds. The atoms are bonding through shared electron pairs so that all atoms in the molecule can pretend like they have a nice noble gas configuration of electrons. Great. We see covalent bonds in a lot of other places though. The gases in the air that we breathe are also made up of molecules in which atoms are covalently bonded. Oxygen gas molecules involve a pair of oxygen atoms bonded together with a sigma bond and a pi bond at the same time, a double covalent bond. Nitrogen gas molecules take this even further by involving a pair of nitrogen atoms bonded together with a sigma and two pi bonds, a triple covalent bond. Let's get a little bit more complicated though. Petrol is also made up of molecules held together by covalent bonds. These are chains of carbon and hydrogen atoms bonded with sigma bonds. Maybe if we add some oxygen and rearrange our sigma bonds, we can also get glucose, a type of sugar. As you might have noticed, things can get pretty complicated with our covalent bonds. You might even wonder how big and complicated our molecules can get. Surprisingly, our molecules can actually get big enough to see and interact with on a macroscopic scale. A diamond can be thought of as a single molecule of carbon atoms all covalently bonded together. Similarly, a car tire is actually, generally, one single molecule. Rubber is one massive network of covalently bonded atoms. Anyway, maybe that's enough covalent bonding for now. Metallic bonding is pretty self-explanatory. If you see a piece of metal, it's got metal atoms all bonded together through metallic bonding. Wires, kitchen pots, coins, all metal atoms bonded together by metallic interactions. There's not really anything complicated to talk about here, at least not until we talk about what metals are good at doing. But that brings us to ionic bonding. Sodium chloride has already been mentioned. This is table salt. Positive sodium ions and negative chlorine ions, or called chloride ions, are electrostatically bonded together in crystals. If you look at iron oxide or the rust that you might find on steel items, the same thing is happening. Positive iron ions are electrostatically bonded to negative oxygen ions, or oxide ions. And for the sake of keeping this explanation brief, maybe we'll stop there. Of course, we haven't even talked about some of the in-between bonds that have a mixture of covalent and ionic character, like the silicon-oxygen bonds in glass. And we haven't even looked at making polyatomic ions, where we have a covalently bonded set of atoms that have an overall charge and act just like our ions from ionic bonding. But anyway, those are maybe stories for another time. We need to start talking about chemical reactions. Right. What is a chemical reaction? It's pretty simple, actually. Chemical reactions generally are processes that occur in which chemical bonds are broken and then new chemical bonds are formed. This works out such that the chemicals, or the types of molecules or materials that you start with, are transformed into different ones as the bonds break and reform. Starting with a simple one that everyone should be familiar with, we can talk about the formation of rust on steel. If you'll recall, we mentioned rust before in our discussion of ionic bonding. In this case, our initial molecules and materials that are going to take part in our reaction, otherwise known as the reactants, are iron metal, which is in steel, and oxygen gas from the atmosphere. Remembering our discussion of bonds, our iron atoms are all bonded to each other through metallic bonds, and our oxygen exists as a diatomic molecule. Pairs of oxygen atoms are bonded together through a double covalent bond. Allowing these two things to perform a chemical reaction together, and oversimplifying how this happens to a great degree, we see the metallic bonds break in the iron metal, and we see the double covalent bond of oxygen break too. The resulting atoms can form new bonds, ionic bonds, to form iron oxide, the product of the reaction. So great, we've just performed a chemical reaction, and it's one that you've probably seen happen. although it's probably not happening fast enough for you to see it directly. We can make things more exciting with a faster reaction though, so let's look at combustion, burning things. The simplest combustion reaction is with the reaction between hydrogen gas and oxygen gas. We described oxygen before as a diatomic molecule in which a pair of oxygen atoms are bonded with a double covalent bond, and hydrogen is similar, but the pairs of hydrogen atoms are only connected through a single covalent bond. Like our rust reaction before, if we allow the reaction between these molecules to occur, we first see the hydrogen and oxygen molecules break apart, and then the broken up atoms will form new bonds to make water. This reaction happens fast enough for us to watch it. We get a flame as the gases rapidly react together.
They are, of course, flammable.
But you might have a certain question if you're particularly tuned in right now. I said that a chemical reaction just involves breaking bonds and then forming new ones. So, why can't these reactions run in reverse? There should be nothing wrong with water breaking its bonds and reforming hydrogen and oxygen gases again, and we should be able to see the bonds in iron oxide break to reform iron metal and oxygen gas. Why do these reactions not happen in reverse? The secret here is energy. These reactions can happen backwards, but we need to think about whether the overall process is going to release energy or absorb it. Breaking bonds always requires energy input, and forming bonds always releases energy. The question becomes, do we get more energy out than we put in? If you do these reactions as I've described, the energy released in the formation of new bonds outweighs the energy that is absorbed in the breaking of the old bonds. Since the overall processes release energy, they're happy to occur. If we do them backwards though, the opposite is true. These backward processes would absorb energy, and so they don't really like to happen. So that's it. It's all about energy. Though this is actually an oversimplification because we also have to think about the entropy of the reactants and products. This also has an effect on which way a given reaction proceeds, and to figure out whether a given reaction occurs forwards or backwards, we need to consider both energy and entropy in a new quantity called the Gibbs free energy, but maybe that's a discussion for another time. We're getting off track again. To jump into some more complex examples and ideas, let's simplify that previous discussion to say that there are certain reactions that can happen under a given set of experimental conditions, determined by this thermodynamics-based quantity known as the Gibbs free energy. There are also some reactions that don't happen under a given set of conditions. Now, if this were universally true, the world would be a pretty boring place. All of the possible chemical reactions would just happen. As a result, our chemicals would progressively release their energy and we'd be stuck with some boring, non-energetic chemicals. Luckily for us though, we don't see this. There's a lot of interesting stuff happening all around us from a chemistry point of view. This is because chemical reactions are not themselves closed systems. We can get non-favorable reactions to happen if we add energy from other sources. A great example of a reaction like this is photosynthesis. Plants are capable of turning water and carbon dioxide into oxygen and glucose, a reaction that would never happen if we just mixed water and carbon dioxide. The overall process would absorb energy, and so it's not favorable. With the addition of sunlight though, and some fancy stuff that plants are able to do on the molecular scale, the necessary energy to get this to happen is provided. The input of energy in the form of light allows the conversion of less energetic reactants into more energetic products. This idea of being able to convert low energy reactants into higher energy products with the right kind of energy input is incredibly useful. If you think about it, it's a way of storing energy for later use in the form of chemical bonds. Plants have been doing it for billions of years, and as a result, we've been left with a nice big chunk of energetic chemicals, or fossil fuels, for us to use to our heart's content and supply all of our energy needs. I'm sure there'll never be any global consequences for using those. Anyway, humans have also figured out many other ways to get non-favorable reactions to happen. Sunlight isn't the only thing that can provide energy from an external source. Electricity is also an energy source that can be used to force these kinds of reactions to occur. Industrially, we use electricity to make a bunch of fancy metals like zinc or aluminium, because the reactions that form these metals are actually unfavorable. Using electricity to do reactions that are unfavorable is kind of the basis of my own channel, actually. I'm interested in using electricity to force chemical bonds to break and reform in ways that they wouldn't like to do without extra energy. There are a couple of practical examples that you could see for yourself if you decide to check out my full videos on the topics. There's stuff like making aluminium metal, as we just mentioned, converting vinegar into a highly flammable gas, or turning common table salt into a much more energetic substance known as sodium chlorate. Enough about my own videos though. Sure, we can use electricity to make chemical reactions happen, but what does that mean? How is electricity even relevant to chemistry, and how does it work in this context? Maybe it's time to talk about that.
And you know what? I think that would be a sweet idea. Maybe it is time to talk about that, but first, subscribe to Harry on YouTube, Scrap Science. This video would completely fall apart if it wasn't for him. I mean, I do like me some good 3D animations, as you can tell, and I do like learning, but I'm not an expert when it comes to chemistry, and without Harry I would just be spreading misinformation. So Harry fixed this video from misinformation to useful information, and I cannot thank him enough for that. So please do be sure to subscribe. And also, if you're subscribing to different YouTube channels, you might as well subscribe to this one. But that's only if you subscribe. And you might also as well subscribe on Patreon if you have some money. But that's beside the point. The point is, you now understand the basics of chemistry. The basics with bonding and other things, pointing a bit more into the electrochemical direction. And there's a reason for it. There is a reason. And that is that right now, it would finally be time to get into